This is one of the most important topics students in honors chemistry and AP chemistry must clearly understand. I will explain this on board on my next video. The school is about to begin. I hope you are enjoying the channel and learning the most important topics in chemistry as very active students. Congratulations! Let's begin. Intermolecular bonds, also known as intermolecular forces, are the attractive forces between molecules. These forces play a crucial role in determining the physical properties of substances, such as melting and boiling points, viscosity, and solubility. Intermolecular bonds are generally weaker than the covalent, or ionic bonds that hold atoms within a molecule. The strength of these intermolecular forces varies, with hydrogen bonding being one of the strongest and London dispersion forces being the weakest. The nature and strength of intermolecular forces are influenced by molecular size, shape, polarity, and the presence of functional groups. Understanding intermolecular forces is crucial for explaining the behavior of substances in various states such as solid, liquid, gas, and their interactions in chemical reactions and physical processes. There are several types of intermolecular forces. London dispersion forces are the weakest intermolecular forces arising from temporary electron density fluctuations around an atom or molecule. Even though these fluctuations are temporary, they can induce similar fluctuations in neighboring molecules, leading to attractive forces. London dispersion forces increase with the size of the molecules and the number of electrons they have. These forces are present in all molecules but become more significant in larger and more complex molecules. For example, noble gases like helium and neon exhibit London dispersion forces. Dipole-dipole forces occur between polar molecules. A polar molecule has an uneven charge distribution due to differences in electronegativity between its atoms. One polar molecule's positive end is attracted to another's negative end, leading to dipole-dipole interactions. An example is hydrogen chloride. The chlorine end of one HCl molecule is negatively charged, and the hydrogen end is positively charged. These partial charges result in dipole-dipole interactions between neighboring molecules. Ion-dipole interactions occur between an ion and a polar molecule. The positive or negative charge of the ion attracts the opposite charge on the polar molecule, leading to ion-dipole interactions. These forces are important in solutions where polar solvents dissolve ionic compounds. When an ionic compound is dissolved in a polar solvent, such as sodium chloride in water, the positive sodium ions are attracted to the negative oxygen end of water molecule, while the negative chloride ions are attracted to the positive hydrogen end. Induced dipole interactions are similar to London dispersion forces. These interactions occur when temporary fluctuations in electron density in one molecule induce similar fluctuations in a neighboring molecule. This results in weak attractive forces. An example is the interaction between two nonpolar molecules, such as diatomic gases like hydrogen or oxygen. Temporary fluctuations in electron distribution in one molecule induce similar fluctuations in the other, leading to weak attractive forces. Hydrogen bonding. This is a specific and relatively strong type of dipole-dipole interaction that occurs when a hydrogen atom is bonded to a highly electronegative atom, usually nitrogen, oxygen, or fluorine, and is attracted to another electronegative atom in a different molecule. Hydrogen bonding is responsible for many of the unique properties of water and is important in biological systems. A classic example is water. The hydrogen atoms in one water molecule are attracted to the oxygen atom of another water molecule through hydrogen bonding, giving the water its high boiling point and surface tension. It's important to note that many substances experience a combination of these intermolecular forces. For instance, a molecule can exhibit both dipole-dipole interactions and London dispersion forces. Additionally, the strength of these forces can vary based on the specific molecules involved and the conditions under which they interact. Intramolecular forces, also known as chemical bonds, are the forces that hold atoms together within a molecule. These forces are responsible for the formation and stability of molecules. There are several types of intramolecular forces. Covalent bonds. Covalent bonds form when two atoms share electrons to achieve a more stable electron configuration. This type of bond is prevalent in most organic and inorganic molecules. Examples include hydrogen molecule. Two hydrogen atoms share electrons to form a covalent bond. Methane. Four hydrogen atoms share electrons with a carbon atom, forming four covalent bonds. Ionic bonds form when there is a transfer of electrons from one atom to another, resulting in the formation of ions that are attracted to each other due to their opposite charges. Examples include sodium chloride. Sodium donates an electron to chlorine, forming Na+ and Cl ions that are held together by ionic bonds. Magnesium oxide. Magnesium transfers electrons to oxygen, resulting in Mg2+ and O2 ions that form an ionic bond. Metallic bonds. Metallic bonds occur in metals, where a sea of delocalized electrons moves freely among positively charged metal ions. This electron mobility gives metals their characteristic property, such as conductivity and malleability. Coordinative bonds. In this type of bond, one atom donates a pair of electrons to another atom. This commonly occurs in coordination compounds and complex ions. An example is the formation of the ammonium ion, in which a lone pair of electrons from ammonia is donated to a proton. Hydrogen bonds. While hydrogen bonding is often associated with intermolecular forces, it can also occur within a single molecule. For example, in a molecule of acetic acid, intramolecular hydrogen bonding occurs between the hydroxyl group's hydrogen and the carbonyl group's oxygen. These intramolecular forces are generally much stronger than intermolecular forces and play a fundamental role in determining chemical compounds' structure, properties, and behavior. A molecule's types of intramolecular forces dictate its chemical reactivity, bonding geometry, and overall stability. See you soon. Subscribe to channel to get notifications.